Welcome back. We're going to talk about informed search methods for the next two videos. So what does that mean? It means that the methods we've been talking about, they don't use any information about any relationship between the node and the goal. And in a lot of map-based cases, you know some information. For one thing, you could just assume that straight line distance exists because it does. And you could use that information. So the informed search methods that we're going to talk about for this module, there are only going to be two of them. Then we'll talk about some more on the next module. Are well, we'll talk about them both in a second. So starting with, we need to talk about what information they can use. We're going to introduce something called f of n, and f of n is the cost estimate for node n. And it's going to be what we use on that graph search to choose a node. So h of n is going to be the estimated cost from the cheapest path from n to the goal, and g of n is going to be the path cost from the root to n. So the first method that we're going to do, before we talk about that first method, what we want to do is we want to update our example. So this is the same example as before, but what we've done is we've added an h of n table. And I'll talk about later where that h of n table comes from. And specifically, it won't even be this video, it'll be the next video. But for right now, I made them up. Again, I made them integers, which as you may see in the next video, might violate some assumptions, but it makes the math a lot easier for examples in class. So h of n is, again, the estimated cost from node n to the goal. So it's not the path cost, it's just the estimated cost of how fast it is from node n to the goal. And you'll note that the goal h of n is 0, because if you're at the goal, you should be at 0. So the first method we're going to talk about, the one that we'll talk about in this video, is called greedy best first search. And it's just a simple change to what we've been doing, where you change instead of a LIFO or a FIFO queue, you use a priority queue. And the priority queue, the score is f of n equals h of n. So that h of n that we just talked about on the previous slide, the estimated cost from that node to the goal, that's what you use. And remember, you're trying to make the minimal path cost. So you use f of n equals h of n, and the lower numbers have the higher priority. So before we give our example, we'll evaluate it. Is it complete? Yes, as long as your space is finite. Is it optimal? No. What's the time and the space complexity? Well, it can be really bad. But if you give it a good heuristic, it's big O of B times M, which is the best that we've come across for the time complexity and the space complexity together. So that's why it can be implemented. Again, it isn't the optimal answer, and probably most of the time you'll end up implementing the optimal answer, but we'll talk about that in a minute. So let's look at the example. I want to say that this example has a lot more information on it than our previous examples, because what I've got here is I've got each search node, and then inside each search node, I have the order in which they are expanded. Sometimes it's on the outside when I ran out of room. And then I have the F cost so that you can see the queue, the status of the queue, because the priority queue could jump to any node at any time. And that's just because if something's lower cost, you would jump there. So it starts at S, and it adds on that F function is 17. That comes from our H function right here. There's S, 17. And then it adds in C and D. And C is 16 and D is 21. And so since 16 is smaller than 21, it jumps down the path to 16. And then it's going to go from C, it's going to add in B and H. And again, H has a smaller F cost, so it goes down H. And in this case, we don't jump back to any other nodes. We just continue to proceed down the path until we get to the goal. And we do get a much better cost than we did with both breadth first and depth first search, but it's still not the optimal path yet. So what are we going to do? We're going to try to fix that in the next search.